Okay, in this section we're going to check the flexure of our anchor beam. So we'll find this in Chapter 10 of ACI 318-11. And we have a doubly reinforced concrete beam section. And we're actually going to analyze it as a singly reinforced concrete beam section. But I've drawn the associated strain, stress, and force profiles for an example doubly reinforced section. We're pretty sure that flexure will not govern given how short the anchor beam is. But we'll go ahead and analyze this as well to be conclusive. And we'll also assume that the bottom steel yields at full compression, so concrete strain of 0.003, so that we can take the load factor phi as 0.9. And we'll have to go back and confirm this. So with the diagram, we can see that we have compression in the concrete and top steel, as well as tension in the bottom steel. And for the ease of analysis, we can take the moment about the centroid of the concrete compression in order to find our section capacity, Mn. And this allows us to eliminate the whole concrete compression term. And here we'll ignore the top steel capacity. Like I said before, it isn't needed for the section and it makes things more complicated. But it is important to have this compression steel for a variety of reasons, such as temperature and shrinkage, and beams with a fixed end condition. Remember from earlier, when I drew the moment diagram for a fixed end condition, how the moment switches signs at the supports. So, like I've shown here, we ignore this, and I haven't drawn out the equation for A, which is the Whitney compression block, so I will draw that out for you here. And we have all of our equations for all of our numbers here based on the properties of the rebar, the properties of the concrete section, which we've defined earlier. We can calculate A, we calculate C, the distance to our neutral axis, and we use B1, beta 1 from the fact that we have less than 4,000 psi concrete. We take that value to be 0.85. And then after we've done this full analysis, we can confirm that our tension steel yields by calculating the strain of the tension steel by this equation here, using similar triangles from this profile drawn above. And then we can confirm by checking that our tension steel is greater than its yield strain. Our tension steel strain is greater than its yield strain using the properties of the steel and its elastic modulus and its yield strain. And then we will finally check that our phi times our capacity, or our factored moment, is greater than or equal to our ultimate moment that the beam is experiencing. And we'll move on to shear.